This problem, we also use Gauss-Jordan elimination to turn this into the reduced row echelon form, or RREF. Right, so Gauss-Jordan elimination, we need to have 1 at the pivot, and then everything to that column turn to 0. So we're going to turn that to 0. Since the pivot in row 1, that's what we base on. Eliminate an element in row 2. So we'll eliminate, add and replace row 2. Right, and we just use the opposite to the number to eliminate. So we use -1. Right, when we do that, row 1 and row 3 will stay the same. One and 3 will stay the same, only row 2 will change. Right, -1 times 1 is -1 plus 1, 0. -1 times -3 is 3 minus 2, so that would be 1. -1 times -17 is +17 minus 12 is 5. -1 times 59 is 59 minus 41 is 18. Right, let's check. Alright, pivot. Yes, everything on that column is good. Now we go to the next pivot. Will be on the next row because we have the echelon formation, remember. Right, and then so that one's good. Now turn this to 0, turn this to 0. We will do those 2 steps. Right, now the pivot is on row 2, so we'll base off row 2. If we want to eliminate row 1, we'll add and replace to row 1. We use opposite number to that to eliminate. So if it is -3, we use 3. Now still based on row 2. If we want to eliminate row 3, we'll add and replace to row 3. And we use opposite to that number. Opposite to -2 is 2. Right. Now we have 1, negative. Right. Row 1 will change, row 3 will change, row 2 will stay the same. Now, row 2. 3 times 0 plus 1. 3 times 1, -3. 3 times 1 is 3, minus 3, 0. 3 times 5, that's 15, minus 7, -2. 3 times 18, that's 54, minus 59, minus 5. Oh, well, I will check with the calculator after this. Now, multiply to row 2. 2 times 0, 0 plus 0. 2 times 1, 2 minus 2, 0. 2 times 5, 0. 2 times 5 is 10. That is 0. 2 times 5 is 10 minus 10, 0. 2 times 18 is 38. 20 is 58. sorry, 2 times 18, 36, 20, that's 56. Actually, it doesn't matter. We'll say in a minute. Right, now let's check. We have one pivot, everything on that column, check. The next pivot is this one, which is 1, good. Everything on that column to 0. The next pivot is going to be here, because the first non-zero entry, right, that doesn't work. There's no way we can make this to 1. So we just have to turn this into 1. That's why I said earlier it doesn't matter, because we just multiply by 1 over 56 to row 3 to row 3. That we turn that to 1 easily. Right, row 1 and 2 will stay the same. Right, now pivot, everything that column is 0. The next pivot is here, everything on that column is 0. The next pivot, which is good, knit that to 0, knit that to 0. So now the pivot on row 3, we will eliminate row 2 to eliminate that, and eliminate -5 in row 1. To eliminate 18, we use opposite to that. To eliminate -5, we use opposite to that. After this two, we should have the answer. Right. So I will only row 3 would stay the same. Right. -18 times 0 plus 1. -18 times 0. -18 times 0, still 0. It's not wrong, but we do that to row 2, sorry. -18 times 0, so that's 0. -18 times 0 plus 1. -18 times 0 plus 5. -18 times 1. And now 5 times 0 plus 1. 5 is 1. 5 times 0 plus 0, 0. 5 times 0 plus -2. Okay, multiply 0, so that's still the same. 5 times 1 is 5 minus 5 is 0. So that is the matrix. So I will use the website to find the reduced row echelon form. So I'm just enter right, and we just calculate and we have the matrix in reduced row echelon form. Right, so whether we use the calculator or that website, we can get to the answer. Bottom line is, this is what we call the Gauss-Jordan elimination. obtain the one in the pivot first, and then everything in that column turn to 0, and then we go to the next pivot so that we maintain the echelon formation. Get 1 and turn everything to 0. And if we want to have 1 when the element is not 1, just divide by it. If we want to eliminate, more likely we multiply to a pivot row and eliminate. By the way, I just want to bring up one more thing. Let's say if we want that to be a pivot, something that is not 0, and it is 0, the only way it works is to swap something else into it. Right. So, yeah, that how to get to those, how to get the pivot to 1. Either we swap a row or we divide by a number to turn that into 1 and then turn everything else to 0. By the way, the calculator or the software, they may not use this. Usually they use partial pivoting, so they pick the one with the largest absolute values. So in that case, the calculation will be less room for error. So like in this example, if we swap row 1 to row 3 and take the 5 as the pivot, because 5 is the biggest values in that column, so if the calculator do it more efficiently and less room for error, that's to move the 5 on the top and use that as the pivot. Of course, after that we still can divide everything by 5 and that is moot. But like I said, most of the problem in this class we have to use reduced row echelon form somehow. So at least we spend a lot of time working on it. From now on, we just use the calculator to get from the matrix to the reduced row echelon form. Right. Now, we can get any matrix into reduced row echelon form. Now, what that reduced row echelon form will tell us, the answer is. Right. Next, a few more theorems before we actually go back to our samples. Right. The row reduction algorithm leads to explicit description of solution. Right. I suppose an augmented matrix of linear has been changed into equivalent reduced echelon form. Usually, I'm just going to add reduced row echelon form so we have the RREF. And my point is, usually that reduced echelon form is RREF because we have a calculator. It takes us the same amount of time to get to row echelon form and to get to reduced row echelon form. So just go ahead and go straight to the reduced row echelon form. Yeah. I said after this section, mostly we only worry about the reduced row echelon form. Hence the REF thing. Right. Now, the matrix or the augmented matrix in that REF, the variable that corresponding to the pivot is called the basic, the others are non-basic variable. So the variable that corresponding to the pivot are called the basic variables. The others are free variable. We'll get back to this in a minute. So, the system is consistent. The solution can be described a basic variable in terms of free variable. We talk about that. We will talk about that. The description of free variable arc as parameters, that called parametric description. We will talk about this. When a system is inconsistent, the solution is empty even when the system has free variable. We will talk about this. Now first, that's what we talk about is the inconsistent here, where we have no solution. Right. So it says here, a linear system is consistent if and only if. By consistent we mean it has a solution, one solution, or infinitely many solutions. That one called consistent. It is consistent if and only if the rightmost column of the augmented matrix is not the pivot column. Meaning, if and only if the echelon form of the augmented matrix has no row of the form. Let's look at the last example. In the reduced row echelon form, let's assume that this is the augmented matrix, so we can just draw a line to separate the coefficients and the constant. Now on this one, what it says, the rightmost column of augmented matrix is not the pivot column. So here we have the pivot here, so that pivot column, pivot here, pivot column, pivot column. The rightmost column is not the pivot column, so this is not the case. The pivot column is not here, so this is consistent. This one has a solution, infinitely or one, but it has solution. On this one, this is the pivot. We have the rightmost column is the pivot column. In that case, no solution. So pretty much if we have a row like this, it has no solution. If a linear system is consistent, then it's either unique or infinitely. Well, we talk about that. Right. Now, how do we write the solution? Right. Suppose we have considered matrix is in the reduced echelon form. By the way, the reduced echelon form is going to be reduced row echelon form. Yeah, it have the reduce in that, so this is going to be RREF. So this matrix is in the RREF form. So what will be the solution? By the way, since we don't have the variables, let's just say x1, x2, x3, right? So this we know is an augmented matrix. The variables corresponding to that, x1, x2, x3, the next one corresponding to the constant. Right, now that is the matrix. Where are the pivots entry? This is the pivot entry, right? And that's all. The first leading one, so that's what we have. So in this case, the x1 is the pivot column because that contains a pivot entry. x2 is the basic because it is it contains the pivot column, contains the pivot entry. So x1 and x2 are basic, and x3 is not a pivot, so it's called free variable. So x1, so we have the basic variable x1 and x2 because they have they contain the pivot entry, or because it is the pivot column. And the free variable is where we don't have the pivot entry. Right. Of course, that is corresponding to this matrix, even though if we that matrix, augmented matrix, is corresponding to this system, even though if we don't have that, we still can solve for that easily. Let's assume for a moment we don't know that. And we just say 1x1 minus 5x3 equal to 1, right? So the first row, 1x1 minus 5x3 equal to 1. And the other one is 1x2 plus x3 equal to 4. Right? So when we write the matrix into this row echelon form, we reduce into these two equations. The last one is 0 equal to 0. That's not really the equation because there's no variable in that. Right? Next, what we see is x3 is the free variable. Free variable meaning it can be anything. So everything will be based on x3 because x3, once we know x3, we know everything else. So in that case, what we do is we're going to solve for x1. We're going to solve for what that is say whenever the system constraint has. Okay. We will highlight basic variables in terms of the free variable. Yep, we're going to highlight that part. That's exactly what we do here. x3 is free, so we write everything in terms of that free variable x3. So we can say x1 is equal to 1 plus 5x3, and we say x2 is equal to what? 4 minus x3. So we write the basic variables as a function of free variables. So how do we write the solution? Right. Our solution is a set of three numbers. And the three numbers we have x1, x2, x3 will be the set of three numbers in the form of x1 is going to be 1 plus 5x3, x2 is equal to 4 minus x3, and x3 is x3, can be anything. Or we write the solution set 1 plus 5x3, 4 minus x3, and x3, where x3 says is any real numbers. Right, so we can have the solution in this case. Everything based on the free variable x3. The basic variable will be solved in terms of that free variable. Now, so this is a parametric description. Everything based on x3. Now, of course, any solution, either we're going to write like this, or like this, or like that. Now, if we just want one particular solution, let's say, for example, if we have x3, I say x3 is equal to 0, then we have x1 is equal to 1 plus 5 times 0, and x2 4 minus 0. So we have the solution is x1 equal to 1, x2 equal to 4, and x3 equal to 0. So if we want to pick one value for x3, we have a pawn as a solution. So this one has infinitely many solutions. Why do we know this? It has infinitely many solutions because it has the free variable. Right, that's the last part here. Infinitely many solutions, at least one free variable. If we want unique solution, one solution, there will be no free variable. So because of the free variable, we can choose freely that infinitely many solution. If not, if we have all basic variables, that will be unique solution. Right. Now let's take a look at these matrices and see what will be the solution. Right. So these are romantic matrix. So just going to put a line here. Now let's quickly check, is this one in reduced row echelon form? Right. If everything is 0, so that's good. 1, everything is 0, 1, so it's good. So this is in the reduced row echelon form. Just make sure that we write in the reduced row echelon form. We have the matrix 1 0 0 0 1 0 0 0 1. Correspondingly to x1, x2, and x3. This is the pivot column. So pivot entry. So x1 is basic, x2 is basic, x3 is also basic because all of them containing the pivot entry. So x1, x2, x3 all are basic. Since we have no free variable, there is a unique solution. By the way, we don't have the pivot on the last column either. In that case, there will be no solution. So this one is one solution. We say 1x1 equal to 5, 1x2 equal to -3, and x3 equal to 2. So those are the solutions. So simple enough, right? When we write the matrix in reduced row echelon form, we can say write the solution easily. Right, so this matrix is that in reduced row echelon form. So let's see. So the pivots here, here, and so this is not 1. So this is not in reduced row echelon form. So if it is not in reduced row echelon form, we're just going to turn that into reduced row echelon form. Right, just use the calculator, turn that into reduced row echelon form. Apply to this matrix 3 by 4, right? 1, 1. Right. So we have to write the matrix in the reduced row echelon form before we do anything. Augmented matrix. The variables. Right. In this case, we see that x3 is the free variable because there's no pivot there. However, what we have here is the pivot column on the last column, on the constant column. If that is the case, this will be no solution because the pivot, the last column, or the column on the right, we'll just say last column, is a pivot column. We cannot have that. If that is the case, no solution. Right. Next one. Let's say if this is the augmented matrix, we have pivot here, here, and here. In the echelon form, the first non-zero entry, all of them are 1, everything else 0. So this is in reduced row echelon form already. Right? You don't have to do much. Just copy that. right? x1, x2, x3, x4. The pivots. Right, first non-zero entry, echelon form, all now 1, everything else in that column 0, so that's good. So x1 is basic, x2 is basic, x3 free, x4 basics. So this will have a free variable. What that means is the solution will be in terms of that free variable x3. Before we do that, let's rewrite this in terms of equation. 1x1, 0x2, 3x3 equal to 5. Right, this one. 1x2, 2x3 equal to -3. And then x4, 1x4 equal to 4. Right, now we will write everything in terms of the free variable. Of course, from here we can say x1 is equal to 5 minus 3x3, right? x2, we solve the basic variable in terms of free variable. x2 equal to -3 minus 2x3. x3 of course is the free variable, so we just say x3 is arbitrary, could be anything, and x4 is equal to 4, and that is the solution. You see, write the matrix as the augmented matrix, write the system as the augmented matrix, turn that into reduced row echelon form, and then we can write the solution from there. Simple enough. And that's what we do. Write the matrix as the augmented matrix, reduced row echelon form, and then just write the solution. We have no solution if the last column is the pivot column. Unit solution if there's no free variable. Infinitely many solutions where we have free variable and don't have to pivot on the last one, obviously. Right, so now let's do more examples. I said the step that we use here, like I said, write the system of equation in terms of augmented matrix, do the reduced row echelon form. I mean, this is more complicated than what it should be. Just turn into the reduced row echelon form, and then we write the solution from there. Simple enough. So this matrix, by the way, you said, if this augmented matrix doesn't look like we're missing something, right? Is there missing something here? Doesn't look like we have enough variable. Yeah, it doesn't matter. Remember, we can always add a row of 0 here if we want to. In that case, x1, x2, x3 constant. If we want to, we can always do that, but we don't need to. Yeah, we can always add a row of 0 so we have a matrix in a nice form and all, but it's not important. Okay, so this is this matrix in the reduced row echelon form. So let's check. We can always add a row of 0, but like I said, we don't need to. 1 pivot, 0 everywhere else. Yes, so this one is in the reduced row echelon form. Once again, the pivot entries, which corresponding to x1, x2, and x3. x1 is basic, x2 is basic, a3 free. Let's rewrite this equation. 1x1 minus 5x3 equal to 2. 1x2 minus x3 equal to minus 1. We will solve for the basic variable in terms of the free variable. So 2 minus 5x3 minus 1 plus x3. So x1 is equal to 2 minus, move to the other side of the plus. So x1 is equal to 2 plus 5x3, and x2 is minus 1 plus x3, and x3 is free, so x3 is arbitrary, meaning it can be anything. We can write that, or we can say 2 plus 5x3 negative 1 plus x3, and x3 is free. Yeah, simple enough, right? Right, next, find the solution to the system whose geometric matrix is this. So we just check to see if it is reduced row echelon form. If it is not, we just do reduced row echelon form. 1. Pivot is 1. Everything on that column is 0, which is good. This is supposed to be 1, so that is not 1, so that is not reduced row echelon form. So let's do that. Reduced row echelon form. Yeah, we just use the calculator to do this. I think we done enough example how to do this by hand. 3 rows, 1, 2, 3, 4, 5, 6. Okay. Right. 1, 6, 2, negative 5, negative 2, negative 4, 0, 0, 2, negative 8, negative 1, and 3. And just 1, 7. Right. So we just said after we do reduced row echelon form, we'll have the matrix 1, 6, 0, 3, 0, 0, 0, 0, 1, negative 4, 0, 5, and 1, 7. Right. This is the geometric matrix. Variables x1, x2, x3, x4, and x5. There's a reason we do not use x, y, or z, because this will run out of alphabet if we do that. Just use x1 and so on. Right. So pivots 1, 1, and 1. Basic, 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 free, free. Right, so we will rewrite this as x1 plus 6x2 plus 3x4 equal to 0, which we solve for it. x1 is equal to 0 minus 6x2 minus 3x4. This will have x3 minus 4, x4 equal to 0, solving for it. x3 equal to what? 4x4 equal to 5, sorry. Won't be 5 plus 4x4 5 plus 4x4, and then the last one is x5 equal to 7, and that's pretty much it. No other way to write. And then x2 and x4 arbitrary. Or we can write the solution as x1 negative 6x2 negative 3x4. x2 is arbitrary. x3 is 5 plus 4x4. x4 is 3. x5 is 7. So that's what we have. Right. Arbitrary. In this class, we usually refer to all real numbers. Right. Next, I'll find a general solution to this system of linear equation. All right. System equation. Why don't we write that as a matrix, augmented matrix, and turn that into reduced row echelon form. Right. Write that as the augmented matrix. 5 for x, 2 for y, 1 for z, negative 11 for constant. 2 for x, negative 3 for y, negative 1 for z, 17 is a constant. 7x, negative 1y, there's no z, 12 is a constant. Now we'll turn this to reduce row echelon form. Apply to the matrix. Oh. Five, 2, 1, negative 11, 2, negative 3, negative 1, and 17. 7, negative 1, 0, and 12. Right? Ah, that makes sense. Right, we have 1, 0, 1 over 19, 0, 1, 7 over 19, 0, 0, 0, and 1. Right. So in this problem, what we have is the pivot column in the last column is pivot column, so no solution. Right, it is very easy to see why the last column is the pivot column. Will give us no solution, because if we're going to write this in terms of equation, what do we have? 0x plus 0y plus 0z equal to 1, and that's not possible, right? We have no x, no y, or no z. There's no way they can combine and give us 1. So that's why it's no solution in that case. So, very simple. Next, find a general solution to the linear equation by finding the reduced row echelon form. Alright, so we write this as the augmented matrix, turn to reduced row echelon form, and we go a solution from there, right? Augmented matrix, 5 for x, 8 for y, -1 for z, 36, the constant, 1 for x, -2 for y, 7 for z, and 18, 3 for x, 1 for y, 1 for z, 21. And just do the reduced row echelon form. Now I'm going to use the calculator as if it is TI-83, where we cannot do everything in home screen. If we cannot do that, we have to go with the edit to input the matrix. If there's something there already and you want to get rid of that, well, go to second plus memory management on number 2, second plus option number 2. Go to matrix, and matrix A, just hit enter and delete. Are you sure to delete? Yes. Now we delete that matrix. Right. Now, if we cannot enter everything in home screen, by that I mean when you hit alpha and zoom, you don't have this menu pop up. That's perfectly fine. Just hit second matrix, go to edit. Now we enter the 3 by 4, 3 rows, 4 columns. Right, 5. Here we can just use enter. The next key doesn't work, so enter 8, enter -1, enter 36, 1, -2, 7, 18, 3, 1, 1, and 21. Alright. Second mode. When we're done, enter the matrix. Second mode to quick. Now go back to matrix again. You see there's a 3 by 4 matrix. If it is under names, we can recall it. Like if I hit enter here, we have matrix A, and yeah, that's the matrix A. Now we will do reduced row echelon form. So second matrix, still go to reduced row echelon form. Second matrix one more time under names A. So we'll perform the row reducing matrix A into reduced row echelon form. Hit enter, and that's what we have. Right, so this is in reduced row echelon form. X1, X2, X3. All of them are basic. No free variable, therefore unique solution. And here we just say X1 is equal to 6. X2 is equal to 1. And X3 is equal to 2. Always just write like this as the solution. So that is essentially the most important in this section is any system of equation, we can write as augmented matrix. From there, we use the reduced row echelon form. And when we look at the reduced row echelon form, whether there is a free variable or not. If there's no free variable and the last column is not the pivot column, so that's unique solution, one solution. If we have the last column is the pivot column, no solution. Otherwise, we have infinitely many solutions, and we can write solution in terms of the free variables. That's what's important in this section. The other is to distinguish between the echelon form and the reduced row echelon form. Well, that's important in this section, but after that we don't really need, because like I said, the calculator just goes straight to reduced row echelon form, so we do that most of the time. And the most efficient way to go to, if we do by hand, to use the Gauss-Jordan elimination to turn the matrix into the reduced row echelon form. So Gauss-Jordan elimination is to get 1 first, the pivot, and then turn everything on that column to 0, and then go to the next pivot, turn everything on that column to 0, and keep doing that until we have no more pivot entry. And once we have the matrix in reduced row echelon form, make sure you know how to write the solution from it. With that, we finish section 1.2. See you in another video in linear algebra. Thank you for watching.